This video is for section 3.4, and we're going to talk about velocity and what the difference is between velocity and speed, and how that all is incorporated to this concept of rate of change. And so our essential question for today is, what does the rate of change physically represent? So rate of change, if you remember back to chapter 2, section 4, we had this term called average rate. And average rate, as we discussed, means algebra slope. So if we look at the word rate, then we know average means algebra. Rate is got to be slope. So the average rate is the slope of whatever is changing. So a lot of times we look at this graphically, and we have to decide, what the axes are. And so the rate of change then is that rise over run. So back from section 2.4, average rate is rise over run. It's our algebra slope. And so here's our rise and here's our run. We need 2 points to calculate that. And so and to get that rise over run. So no calculus involved at all for that concept. So when we look at this new concept here, instantaneous rate, we know the rate means we're looking at a slope, and instantaneous means 1 point. So if it's 1 point, then it's taking the limit of this expression. And we know that when we take the limit of this expression, we're talking about setting ourselves up and allowing this to move back to the 1 point. And so we're going, if we run this animation, we're not talking about average anymore. We're talking about instantaneous rate when we're talking about the slope at 1 point here, this orange point. So the instantaneous rate of change is looking at that slope at that single point. And if you remember back from 2.4, the slope at a single point to the curve, or we just call that the slope of the curve, is the derivative. So the instantaneous rate of change then is the derivative. That's the slope at a single point here. And so now we have these two different types of rates. One involves calculus and one doesn't. So our instantaneous rate of change involves calculus. That's our derivative. That's our steepness of our curve. And the average rate does not. So when we talk about the slope of whatever is changing in relationship to the term rate, a lot of times we think of a rate as with respect to time. And a lot of times they are, especially when we're talking about velocity. But really, we can talk about the rate of anything changing with respect to any variable. So x and y, we're going to represent the x and y quantities with a variety of descriptors. And I'll get more into that as we go through this presentation. So the definition of the slope of a curve at a point. This again is back from Unit 2. We're talking about allowing that slope at a point. So we're talking about taking the limit and allowing that these 2 points to come together so that we have the slope at a single point C. So if I try to stop the video right when it's at a single point here, that is instantaneous. If you think about the word instant, instant means 1 point in time. So so there's our slope, or our steepness of our curve at a single point. We know that to be the derivative. So we don't really necessarily have to. We have a variety of things we can we can identify in terms of rates of change. For instance, here's a cross section of a tree. And we know that if we count the rings on a tree, that each ring stands for a year of growth. So if we look at this cross section of the tree, the first year of growth, there's this really dark dot in the middle, and then just kind of, we know the growth does not occur evenly. We have years where we have little growth, and then we have years where we have lots of growth for different reasons. Rainy seasons, typically more growth. Dry seasons, typically less growth. So the question here is to find the rate of change of area with respect to its radius. So how is this quantity changing with respect to this quantity? So if we graphed the radius versus the area, then we can get an idea of the instantaneous rate of change. So that means then, if we're talking about instantaneous, we're talking about taking the derivative. And so now what we're going to do, focus on in this section, is taking the derivative of something, but we're taking it with respect to with respect to a variety of variables. Usually we'd have a dx down here and a dy up here. All we're saying here is that the function y is area. It's a physical quantity, and we're differentiating that area function. Here it is. We're differentiating that area function with respect to the variable it's written in. So that just means doing the power rule on variable r. So what we're doing is we're going to do the power rule on variable r here. So the pi is going to come out in front, and then we're going to differentiate r squared. And so we're going to get 2r. So the instantaneous rate of change of area with respect to radius is 2r times pi, or just 2 pi r. So like I said, it's taking the derivative, since we're talking about instantaneous. That's the rate of change at one point, and we're taking the derivative with respect to a variety of variables depending upon what we are monitoring. So this would be a situation where we go out and measure the radius of the tree from the center to the edge each year, and we calculate its area and we graph that. So if this is the instantaneous rate of change of area with respect to radius, then if we evaluate that when the tree has a radius of 5 inches, so you think about that, that's a diameter of 10 inches, then the instantaneous rate of change is going to be 2 times pi times 5. So we're just evaluating. This is what the symbolism means, this vertical line with r equals 5 literally just means substitute 5 into your derivative and evaluate. So the rate of change of the area of this tree is 10 pi inches squared per inch. Let's take a look at these units, because this is where units kind of become important and where this came from. Think about the units itself as a fraction. So the top indicates what is changing in the top of my derivative, and the top of my derivative, the area is changing. So the units for area are inches squared or units squared, and the bottom of my fraction is with respect to radius, and we measure radius in lineal increments, so like inches or meters or centimeters or something like that. So the technical units for rate of change of area with respect to radius is inches squared per inch. If we would simplify this and just write inches, which we could because of how we deal with, how we deal with the units in the same fashion, it would be okay, but we would lose the significance of what these units mean. So we typically don't simplify the units at all. We typically just leave it as 10 pi, which is about 31 inches squared per inch, just to reinforce the concept of the instantaneous rate of change of area with respect to radius. If we want to evaluate the instantaneous rate of change of the area of this trunk with respect to radius at 10 inches, so this is when the tree is 20 inches across, the diameter is 20 inches across. I think I have a typo here. There should be a 10. Then we're just going to put 10 in here, and we have 20 pi inches squared per inch. So we have an instantaneous rate that's twice as big for a tree that is now twice as wide. So let's talk about another rate now, and motion along a line. So you know, you've done in physics, you've done the buggy lab, I think. That would be the motion of a buggy along the ground, or we could just say along a line. And so when we typically talk about motion of something, we typically talk about graphing its position, where it is, at a specific point in time. And so we typically call the position function S of t. So this is function notation. S stands for position, and the t stands for time. So the t would be on the horizontal axis, the s would be on the vertical axis. So we have something that looks like this. So we have motion here in miles per hour, which means we're probably driving a car, not a buggy. And so let's talk about displacement. So we're going to talk about some physics-related quantities here. Displacement is how much we've moved, right? So how much our position has changed. So if we look at this, our displacement is this vertical physical quantity of the graph. Okay, we started out at this position and we ended up at this position. So our position can be defined then as our displacement, excuse me, can be defined as our position, our final position at B minus our initial position at A. The average velocity then, again, you see the phrase average, you know velocity is a rate. So we have to look at average velocity as an average rate. Then we're talking about our algebra slope. So if we had to highlight this, we would highlight average velocity, average rate, algebra slope. Those are all meaning the same things. So we know we're talking about rise over run. So our rise is our change in position, our displacement. Our run is our change in time. And we, again, just to reinforce this, we need 2 points to calculate this. So to calculate this, we'd look at our change in position and divide it by our change in time. And that's our average velocity. That's like drawing a straight line between A and B. There it is. So that's that line right there represents the physical quantity average velocity, or average rate. And so its units would be miles per hour, right? We have position on top and time on the bottom, so the units just follow the numbers. Let's talk about instantaneous velocity. So the instantaneous velocity, and this doesn't animate, but it would be like taking point B back to point A, and that would be then the derivative. So we would draw then our tangent line at A. So this is our instantaneous velocity at point A. And we would have the slope of that tangent line, and we could find the slope of that tangent line by taking the position function and differentiating it and then evaluating it at A. So this is different than speed. Speed is measured on your speedometer, and speed does not give you any indication of direction. So when we take a look at the speedometer, it's just going to give us a number, and it's not going to indicate our direction. So our direction comes from the fact that this slope, depending upon where we are in our position curve, could be positive or negative. But the speedometer is not taking into consideration the fact that that slope can be positive or negative. So all the speedometer is doing is saying, let's get our velocity at point A, and whatever it is, let's make it positive. Let's just take the absolute value. And that's our speed. That's what our speedometer would say. So we know that velocity is a rate because it's in meters per second or miles per hour or inches per hour or something like that. And so since this is a rate, we know this is the first derivative. And it's the first derivative of what function? It's the first derivative of position. So, and then we can go on to say that speed is the absolute value of the velocity. So speed is saying, let's find the velocity, let's get its value, and then let's take it, the absolute value of that. So we have a card that I'll put up on the calculus board, just to remind you of our definitions of instantaneous velocity and speed. Notice we don't have a card for average velocity because we defined that back in Chapter 2. So you'd have to look at the earlier cards to get that average velocity card. But it's there. So let's take a look at another rate. So acceleration is the derivative of velocity. So it's the rate of change of velocity. So it's a derivative of a derivative, which means we can call it the second derivative of position. So if we take a look at that, this is our higher order derivative. So the acceleration is the rate that the velocity is changing. So if we take a look at our instantaneous velocity at A and our instantaneous velocity at B, trying to get both of them to show up here. There's our instantaneous velocity at A, and as it travels along, as my tangent line travels along to the instantaneous velocity of B, you can see that it got more vertical. So what we need then is it's the rate, the quickness or slowness with which the speedometer in your car is changing. So we have a tangent line at A that's flatter than a tangent line at B, so we know our velocity is increasing. And it's the rate at which it's changing. So it's how quickly is it increasing. So for that we need to take the derivative of velocity, which is a higher order derivative. So because velocity itself is a rate, so it's the derivative of position, or we call that the second derivative. So let's try to apply some of these higher order, these instantaneous rates and higher order derivatives to a question here. So we have a particle moving along the line, and its position at time t equals 0, it's a typo, is given by this function. So it's a cubic, and that describes where it is at any point in time. And so it looks kind of like this. So that doesn't mean the particle is moving back and forth. That just means that the particle at time t equals 0 starts right here at 10, and then it moves away from us and comes back towards us and then passes us and even passes the origin and goes into the negative positions. And then it turns around, comes back to the origin, comes back to us, and then goes beyond us. So it says find the displacement in the first 3 seconds. That means we need to find our position at 3 seconds. So if here's 3, we're right here. I think we're at 0. And we started at 10. So the way we find those values, if we don't have a graph, is we plug in 3. And we get a final value here for the position. So we've got 27 minus 81 plus 45 plus 10. And that equals 1. So I was off a little bit. We're up here at 1. So our position at time t equals 3 equals 1. And at t equals 0, when we plug in zeros for all of this, we get a position of 10. So here's our initial position, here's our final position. So the displacement goes from this value to this value. So our displacement is our final value minus our initial value. So it's 1 minus 10. So our displacement is minus 9, which means that we started here, and in the first 3 seconds, this object moved away from us to the right, and then came back past us to the left and ended up at the location 1 on the number line. So it moved, even though it did a little back and forth in the first 3 seconds, by the time we got to the 3rd seconds, it was 9 meters to our left. Let's find the average velocity over the first 3 seconds. So in this case, we need our change in position over our change in time. And we have our change in position from part A. Our change in position is final minus initial. Our change in time is 3 seconds. So we have a minus 9 change in position, minus 9 meters. We have a 3-second time interval, so we have a negative 3 meters per second for our average velocity. So we moved left 9 meters in 3 seconds, so our average velocity is negative 3 meters per second, which is the slope of this line. If we go down 3 and right 1, down 3, right 1, down 3, right 1, that's our slope. For C, it says find the instantaneous velocity when t equals 3. So right here, I want to know the steepness of this curve. So I'm going to need the derivative. So let's take a look at this function and differentiate it. So this would be 3t squared minus 18t plus 15. So there is my velocity function. And now I can go ahead and evaluate that when t equals 3. So I plug 3 in for here and here. So these are the ways to represent that using either the velocity function or the derivative of position function. And so as we plug 3 in here, we get 27 minus 54 plus 15. And that's going to be minus 12 meters per second. So that means the steepness of this curve, or the slope of the tangent line, is sloping downward, sloping in the negative direction, 12 meters per second. For part D, so if we take a look at this, actually, before we move on to part D, this was our average velocity. This is our instantaneous velocity. Our instantaneous velocity shows us what's really happening. The average velocity kind of doesn't. It's kind of like we close our eyes for 3 seconds and we don't care what happens. Part D then is acceleration. So this is the higher order derivative. So we're going to have to take, and this is out of order, we're going to have to take the derivative of this. This is really out of order. Pardon that. Hold on here. Let me just get, there we go. So differentiating this, so ignore this for a second. Differentiating this, we're going to have 3 times 2 at 6t, and then minus 18. And then if we want the acceleration when t equals 3, so we're still talking about this green dot here, we plug in a 3, and our acceleration is 0 meters per second. So at this location, we have no acceleration instantaneously. This is actually a really specific point, and we'll talk more about it in the next unit. But it's where our acceleration is instantaneously 0. For part E, it says at what value of t does the particle change direction? So when we change direction, that means we're turning around. So we turn around here. We're going from away to coming back. And then we're here, same thing, we're going from away to coming back to our original position. So if you notice, that happens at the hills and the valleys. And we know the derivative at the hills and valleys. The derivative at the hills and valleys is 0. So, so we're going to have to take our derivative, which is from part C, and set it equal to 0. And so if we take a look, as I have here that the particle changes direction when the velocity changes signs. So think about a number line, and think about velocity as just values. If we go from positive to negative, we had to have passed through 0. And that's this location. That's where our slope or instantaneous rate is 0. And at this position, again, our slope or instantaneous rate is 0. So here's my derivative. I'm going to set it equal to 0. And I'm going to, we did this in the last section, in section 3.3. Right? When we set the derivative equal to 0, that's how we're finding our hills and our valleys. That's how we're finding the situation where our slope or our tangent line is horizontal. And so I see this trinomial, three-termed expression that I need to solve for. And of course, when I see a trinomial like this, the first thing I should be thinking about is factoring. So the first thing I look at are the coefficients, and if I can reduce those coefficients or not, and I can pull out a 3. And so I would prefer to factor out a 3, but in this case I divided. So we're really trying to factor t squared minus 6t plus 5. and that factors into t minus 5 and t minus 1. And so you might kind of be able to pick those off the graph. And here's my t is equal to 1, and here's my t is equal to 5. So 5 and 1, 5 seconds and 1 second are when we are turning around or changing direction. You can almost pick those right off the graph as you're looking at the graph. So part F then is, what is the particle's position when it changes direction? So again, we could almost pick this right off the graph. Its position here looks to be about 17, and the position here looks to be about minus 15. But really what it's saying algebraically is find the position at time equals 1 and find the position at time equals 5. So plugging in those two time values back all the way back here into our position function, we get a position of 17. We can confirm that on the graph. And then plugging 5 in here. So notice I have this tangent line. There's the turning around. Velocity equals 0, and that corresponds to a y value of 17 on the position graph. And then when I plug in 5 here, I get negative 15. So again, here's my tangent line, my horizontal tangent, and that corresponds to a position of negative 15 on the position graph. So at this point, you should be able to do the day 1 homework in WebAssign. If you're looking to do a Blackboard quiz, wait till we're done with day 2.